Greetings and welcome once again to my new calculus channel. My name is John Gabriel, and this is, would you believe it or not, the third video and probably the last one in this series on axioms in sound mathematics. So, seeing I'm on a roll, I'm going to try and complete the last and fifth requirement in this video. Now, there are some things I would like to correct, and in my previous video, first of all, I misspelled supplementary. I put an I there, but it's actually an E. And the proof that supplementary angles have a sum of two right angles or a semicircular arc is given by the fact that a semicircle consists of equal angles, which we called right angles, okay? And that was proved in the previous video. So therefore, any combination of angles on a straight line, which in my demonstration has been the diameter of a circle, has a sum of two right angles, okay? The original Greek definition of line and plane in book 1 is not as rigorous as the one I described in the series. So in Euclid's Elements, they don't use a circle to, well, Euclid doesn't use a circle to define a plane. He just says a plane surface is one that lies evenly with straight lines on itself. Now, that's not a good way to do it, because in order to imagine that, you'd have to fast forward ahead to new geometric objects like curved surfaces such as this, and then only in this case can you imagine there not being any straight lines that lie evenly on the surface. For example, this is a sphere and this is just a symmetrical curved surface, all right? So Euclid didn't really do it the right way, all right? And this here would be self-referential because you have to have the existence of those objects. But I don't do that. I go from one requirement to the next, and I adhere strictly to those requirements. So, and then also, a line does not consist of points, all right? So a line is, you'll also find a bit of a confusion here in the first few definitions, because it first says, and a line is a length without breadth, and a line has extremities that are points. And, well, strictly speaking, and then again, a straight line is one. So three definitions which are online, which actually I've done away with. It's a line is simply the distance between 2 points, all right? So we can take that as a better definition. And also the Greek word for point, by the way, simio, sounds very similar to the word for flag, which is simea. Okay, simio and simea. And really, if you think of points along a line, they're like flags or road signs which indicate distance, okay? Now, as I said earlier on, to say that something lies evenly with something else requires a lot of prior knowledge of more advanced geometrical structures which may not be in place. And in this case, they were not in place. So to define the circle after the plane is incorrect if we are to use prior requirements. Okay, so I don't need that. Actually, I'm going to just hold on to that for a second, but I did mention it. Now, let's get back to the presentation. And the first requirement states, by the way, that the sum of cointerior angles on either side of a transversal crossing any two lines is constant. That is what the fifth requirement states. It says nothing about parallelism. And if you look at Euclid's Elements, the fifth requirement is stated over here, and it says, and if a straight line falling across two straight lines, etc. But nothing in there about parallel lines, and also in the Greek, there is no mention of parallel lines. The Greek is on the left-hand side here. It says, ke an is δύο ευθείες, ευθεία, επιπτούσα τας εντός και επί τα αυτά μέρη γωνίας δύο όρθων λάσονας ποιή. And ekvalomenas, etc. So there's no word there which says anything about parallel. Okay, the Greek word for parallel is parallelos. All right, so the fifth requirement in the original Greek is stated without using the word parallel at all. And now we have to derive this concept here from the previous four, okay, that the sum of the cointerior angles is constant. So before we can do that, we need to have what's called a theorem. And watch how I'm going to do this, because it's very ingenious. So again, I'm not going to use any arithmetic, only the joining of arcs on a circle circumference. And this is what Euclid is saying. He's saying that the sum of this green and blue is constant. Doesn't matter how you move this line. So for example, you see the sum of these two angles. Doesn't matter how you move the lines and whether they're parallel or not, this remains the same. Okay? Doesn't matter what you do. You see that? You can move those, and you can even move, well, let's see if I can move this here. I'm sorry, I'll have to do that. You can do that, and it doesn't matter how you move them, it stays constant. Okay? So the fifth requirement states that as long as the red line, this transversal, crosses both the blue and the green lines, the sum of the yellow and red angles remains constant. Also, the sum of the blue and green angles remains constant. To prove that the fifth requirement is true is fairly straightforward. Since the green, blue, and black angles are part of a triangle, which, by the way, we saw from a previous video, rests on a circle, their sum is two right angles, okay? And therefore, the blue and green angles will always be supplementary to the black angle, and hence their sum cannot change, because these two angles here will be supplementary to the black angle, and likewise, also, by transitivity of equality, these will also have a constant sum, since they depend on the green and the blue angle that you see here. So their sum cannot also change. As you can see, we have already 26 pages to demonstrate the systematic derivation of the 5 requirements. So using only straight lines, we can complete this systematic derivation of the number concept, and you can see how I do that. And this is entirely different now. This moves on to what the meaning of the number concept is, and how we got numbers is also part of my free ebook, and also an article on LinkedIn. Okay, so now I'm certain that the ancient Greeks were able to systematically derive all the requirements as I have done, and this means they are not axioms. So you've often heard by many incorrigible baboons in mainstream academia that you need axioms in mathematics. You don't, okay? And I've shown you now also through this whole presentation of approximately 26 pages that you can derive everything systematically, and that if some alien being had to start off in the way we did and continue the same way, they'd also derive the 5 requirements, not axioms. All right? So that's pretty much it, and I think I'll stop again here because I'm practically done. I would like to encourage you to subscribe, to click like, to share the news with your friends, and I hope you've enjoyed this 5-part series. I've purposely tried to complete it as soon as I can because I usually don't feel well on most days, and today I've really been feeling pretty good. So I think that's it for now. Write me a question in the comment section if you have one, and I'll try to answer it as soon as I have the time. This is a new calculus channel, and my name is John Gabriel. Till next time, good.